Using our equilibrium description of solubility or dissolution, right, things dissolving, we want to look at defining molar solubility. So molar solubility is the maximum amount of stuff you can get dissolved into a pure solvent. So this is going to be a concentration in molarity. So this is true for everything. It doesn't matter if your salt is soluble, insoluble, there is going to be some maximum concentration that you can get, and that corresponds to what we call a saturated solution. So there's the maximum amount of dissolved solute added at a concentration. If you add more salt or whatever you're trying to dissolve, it's not going to dissolve. It'll stay just as like a solid clump. The value of the molar solubility is directly related or determined by the value of KSP. So they go back and forth, right? KSP says how much product you're going to make when you're dissolving. So molar solubility is quantifying that amount, how much stuff dissolves. And so molar solubilities are defined for everything, right? So silver chloride is insoluble. So that means kind of historically, you put in your solid silver chloride and very little of it dissolves, right? But some does, right? You do get some silver and chloride ions out in solution. It's just the maximum concentration is 1.3 times 10 to the negative fifth molar. So very, very low. And importantly, like not really chemically useful. You're not really doing much. You can't really do much with those silver cations. Sodium chloride is very soluble, so its molar solubility is 6.2 molar, right? So in that case, yeah, you put in your sodium chloride solid and a bunch of it dissolves. Now, this is still the max. If you have a solution of sodium chloride that's 6.2 molar, if you add more in, nothing happens, or it doesn't dissolve. You get that solid that stays down in the solution, right? It just kind of collects at the bottom of the beaker. So there's a maximum. That's obviously still a very high concentration, right? 6.2 moles of sodium chloride per liter of solution is very, very high. That's a lot of sodium chloride that you've gotten dissolved in that water. And so, but it is not, you can't go beyond that. But you can certainly do a lot of chemistry. It's really affected. This is very different than pure water, right? This does not have the properties of pure water. It conducts electricity. It has a very different density, all that. This solution, the silver chloride, that still has basically the properties of pure water. Also important to note when we're defining these molarities, really what we're talking about is basically the amount of solid that's dissolving. So you're really kind of describing how much solid can you get dissolved, or liquid if it was a liquid solute, but how much of the solute can you get to dissolve? Let's work an example. The molar solubility of magnesium hydroxide is 1.65 times 10 to the negative fourth molar. What is KSP for magnesium hydroxide?
All right, the molar solubility of magnesium hydroxide is 1.65 times 10 to the negative fourth molar. What is the KSP for magnesium hydroxide? Okay, so we want KSP, and in this case, I want the number. I want the value for KSP. And so the question would be, well, what's my equation for KSP? You know that for any salt, if we're given the molecular formula, so magnesium hydroxide, we know that we can predict how it will dissolve. And so if we can predict how it will dissolve, we can then come up with the equilibrium constant for this equation, right? So that'd be our solubility product, concentration of magnesium, concentration of hydroxide. Oh, and that should be squared, sorry. The concentration of hydroxide, because there's two right there. So there's our equilibrium constant expression, our equilibrium constant expression for dissolving magnesium hydroxide. We call it the KSP because it is dissolving a salt. And so if we wanted to know the value of KSP, we just need to plug in the values of these. So what we need are concentrations at equilibrium. And we know how to do those. We use an ice table. So we want to go from we want to determine these amounts of ions dissolved at equilibrium. And that's going to give us, this idea, this kind of correlation into KSP. And so we want to get that from an ice table. So how we can set that up: magnesium hydroxide is with magnesium 2 plus 2 hydroxides. And so we know that the magnesium hydroxide is a solid, so that's not going to show up. So what we're looking at is really the dissolving, right? The actual dissolving of this salt. And so the magnesium, well, that we say dissolved, we basically have none of those. We have none of the dissolved magnesium present, or hydroxide. We're basically imagining you have nothing, right? You have just a salt, a solid salt. You're going to allow it to dissolve in water. So initially you have no dissolved ions. So how many ions do you have at equilibrium? This lets us set the zeros over here. We can then predict the shift. We want to be sure those shifts, we're always going to be plus, we're always going to be shifting to the product side. We want to be sure to get coefficients. So the 2 hydroxides becomes plus 2x. So the concentration of magnesium would be x, and the concentration of the hydroxides would be 2x. And so what we can do with that is we can take those and we can plug those expressions in for KSP, right? Because this tells us that the concentration of my magnesium is x and the concentration of hydroxide is 2x. Okay? And so we could take those and plug them in, and we would get that KSP is equal to the x right here, and then 2x squared. So the question is, where does x come from? Right? And if we think, or what is the value for x? Because that's what we really would need to plug in to get the value for KSP. And that x is going to be equal to our molar solubility. This tells us the molarity of the magnesium hydroxide that would be there. And so basically that tells us 1 mole of this gives us 1 mole of magnesium and 2 moles of the hydroxide. So x is always going to be your molar solubility. So what we can just do, we can simplify this. Don't forget the 2 goes to the second power goes to both of those. So we get that KSP is 4x to the third, because it's the squared power right there. 4 times the solubility is 1.6 times 10 to the negative 4th molar. To the third power. We would then get that KSP is equal to 1.8 times 10 to the negative 11. And so we can see that there's going to be this relationship. Molar solubility is telling you how much total of the salt dissolves in the water. KSP gives you a relationship between the dissolved ions. Okay, and so they're always going to be related by the ice table setup, and your x will always be equal to the molar solubility. You will note molar solubility is not equal to KSP because you have this algebraic relationship. We can always come up with that algebraic relationship using an ice table.
So when we're talking about molar solubility, we always want to be mindful that we're talking about the overall compound. So when we're looking at something like magnesium hydroxide, when we say that the molarity, the molar solubility is 1.65 times 10 to the negative 4th molar, that's a description of the number of moles of the compound magnesium hydroxide that we could get to dissolve in 1 liter of water. We know that when magnesium hydroxide dissolves, each mole makes 1 mole of magnesium and 2 moles of hydroxide, right? So the total number of ion concentration will be higher, right? We can use that stoichiometry, the 3 right there, to come up with the fact that it's a higher concentration of total ions. So when we're talking about molar solubility, we're just looking at what of the compound would dissolve, how many moles of magnesium hydroxide dissolve. Then there is the other impact of like, well, how many ions, the concentration of ions is going to be a higher quantity. Because you don't care, they're just ions independently floating around. Participation 1024, question 2. What is the molar solubility of PbCl2? KSP is equal to 1.7 times 10 to the negative fifth. So the second question on participation 1024, due Friday, October 24th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the molar solubility of PbCl2? Equilibrium constant for that is 1.7 times 10 to the negative fifth. All right, 2 questions down already, 2 participation questions across 2 videos. I don't think we'll keep that pace up, but who knows? See you in the next one.